Good morning, guys. Today we're going to be looking over the minimum spanning tree, which involves networks in Unit 4. Essentially what we want to do is connect all vertices to a system, and the best example I like to use is a water pipeline or even an electricity cabling system. We want to install them in the cheapest possible manner, whether that be the shortest or the cheapest. Generally, I'd say the cheapest. So, this is an example, and you can see the question's referring to cost. What is the cheapest cost to ensure all vertices are connected? So to begin this question, we're going to assume that A is connected to the system, and that way we can use it like a logical series of steps to work our way across. So we're going to connect A to the system. Then we can say, well, we can either connect B or C. Initially, we might think that the quickest way to get from A to C is through this 12, but if we actually look at connecting A to B first, which is shorter, and then B to C, so because we would have had to have connected B anyway, if we did A to C, then we would have had to have gone the 7 anyway. So it's the difference between 12 and 7, which is 19, and 11 and 7, which is 18. So all three of these needed to be connected, and 11 and 7 are the smallest of those values. And then from then on in, you can do the same. You can think, okay, well, to connect E, is it going to be cheaper to go with the 22, or because we're already at C, C's already connected, can we go 16 and 8? Or you might even be able to go a little bit further around. So I'll let you guys have a quick look at this when you get a chance. Notice that when I connected E, I didn't have to move from E. I could have chosen to go back and then continue from D. Because this is just the shortest path. All values need to be connected. It doesn't have to be traversable. We just need to connect everything in the shortest possible way. If you have the luxury of a table, or if you think you have time to create this table, which would take a long time, we can use what's called Prim's algorithm, and it runs on a pretty similar system that we used in the visual on the network. We're going to assume that A is connected. So we don't need to consider any of these horizontal values. So the start is the hardest part. That's why I've got a little note down here about how to start. So we've connected A. We're going to denote that with a tick. Then we think, okay, which one of these are the smallest that we can connect A to the next vertice or the next vertex, and that's E. All right, so we're going to connect A to E. Then we can delete that row and consider to ourselves that E is now connected. Now what we can do is we can actually look down the A list and the E list and look for the smallest value to connect the next vertex to this network. And it looks like it's going to be C here. So now we've connected C, we circle that one, we delete that row, and we tick C to say, yes, that is connected to the network. Now we can look down A, C, and E, and we can look for the smallest value. Looks like it's going to be 360 by connecting G. All right, so now we can delete that row, circle that value, and tick G. G is now connected. We can look around for the smallest value. Looks like it might be F. So we delete the row, circle the value, tick F. Now it looks like we've opened up this one, which is very short, so we're going to connect D after we've circled, erased. So circled, erased, and ticked. Okay, we've connected F, circle, delete the row, tick F, and then finally all we need to do is connect B by looking through here. The smallest one is F to B, and then we do the same. So now we know which values are going to be connected by which of these dollars or routes, and just checking that we've connected all values to the system. Thank you very much for listening, guys.